Why do some transformer architectures train smoothly, while others suddenly diverge? The answer often lies in signal propagation at initialization, specifically, how gradients are amplified or attenuated as they flow backward through the network. Today, we're diving into a deep technical analysis of normalization-free transformers. We'll explore how replacing standard LayerNorm with tanh-like nonlinearities, such as dynamic tanh or dynamic ERF, often called Derf, fundamentally changes the stability of deep networks. To understand this, we first need a way to measure gradient behavior. The researchers use a metric called the Averaged Partial Jacobian Norm, or APJN. Essentially, the APJN provides a scalar measure of how much a signal is amplified across layers. In a critical regime, the APJN grows according to a power law, meaning the signal neither vanishes nor explodes exponentially. This is the gold standard for stable training. Now let's look at the architecture. In a standard pre-LayerNorm transformer, we have alternating blocks of bidirectional self-attention and MLPs. The pre-LN setup is known to be robust because it maintains this criticality across a wide range of initializations. But what happens when we remove LayerNorm and replace it with an element-wise nonlinearity like Derf? To answer this, the authors extended the APJN analysis to transformers with bidirectional attention and permutation-symmetric input configurations. They derived recurrence relations to track how the activation statistics, specifically the self-dot product and cross-positional dot products, evolve across layers. The findings are striking. While pre-LN models exhibit power law APJN growth, these normalization-free models exhibit what is called stretched-exponential growth. In the language of signal propagation, this is a subcritical regime. Technically, the difference comes down to how the Jacobian of the nonlinearity behaves. For LayerNorm, the variance of the Jacobian scales as the inverse of the activation variance. This leads to that stable power law growth. But for tanh-like nonlinearities, the Jacobian decays much more slowly, roughly as the inverse square root of the variance. Because the activation variance grows linearly with depth, this slower decay results in a much more aggressive, stretched exponential amplification of gradients. The theory also highlights the role of the parameter alpha in Derf. Alpha acts as a scaling factor for the nonlinearity. A smaller alpha reduces the effective contribution of the residual branch, which slows down the growth of the APJN. Essentially, by tuning alpha smaller, you can push a subcritical Derf model back toward a more critical pre-LN-like regime. But does this theoretical, gradient amplification, actually manifest as training instability? The researchers tested this using vision transformers on the CIFAR 100 dataset. The empirical results match the theory almost perfectly. First, they found that Derf is significantly more sensitive to model depth than pre-LN. While pre-LN maintains a constant convergence rate as you add layers, Derf models hit a critical depth boundary where they simply fail to converge. Second, Derf is far more sensitive to weight initialization. If you increase the standard deviation of the initial weights, Derf models become unstable much faster than pre-LN models. Finally, they looked at the trade-offs of tuning alpha. While decreasing alpha improves stability by reducing gradient amplification, setting it too low, for example, alpha equals 0.1, actually slows down convergence. There is a sweet spot, where alpha is small enough to prevent explosion but large enough to allow the network to learn efficiently. There is one last critical detail, the final normalization layer. In pre-LN, the final LayerNorm keeps the output scaled. In Derf, the final layer is also a tanh-like nonlinearity. Because the variance of the activations is highest at the final block, this final Derf layer can further amplify the backward gradients, making the optimization even more sensitive to the choice of alpha and weight scale. In summary, replacing LayerNorm with element-wise nonlinearities shifts the transformer from a critical to a subcritical regime. This results in stretched exponential gradient growth, which explains why these normalization-free architectures require much more precise tuning of hyperparameters and initialization to achieve stable training. For those implementing these models, the takeaway is clear. If you're moving away from LayerNorm, your initialization strategy, specifically your weight scale and your alpha parameter, is no longer just a detail. It is the primary determinant of whether your model converges or diverges.